everyone, I'm Kenny Madrigal and I'm the project chair for IEEE at the University of Houston for the academic year 2025 to 2026. With my introduction out of the way, let's start talking about what this workshop is about, which is about designing and fabricating printed circuit boards. So, this workshop is extremely beginner friendly in my opinion because we're going to walk through all the steps that are required before we get to making a PCB for the first time. A PCB is a circuit board that looks kind of like this example picture I've put on here. But yes, let's talk about it. When you want to make a PCB, before you actually design it, you need to make sure that your design will actually work, right? So you can use tools such as breadboards to put your components on there as a test and make sure that your circuit works as intended. And then you can move on to making a schematic for your prototype that the computer can then turn into connections on a PCB. And again, if these words don't mean anything to you right now, they will after this workshop. So let's begin. For this workshop, I'm using a simple LED blinker circuit, so it just has a 5x5 timer, some potentiometers, and we'll get to that in a second. What I'm trying to demonstrate in this video is that this is the way that all the components need to be connected for it actually to work as I wanted it to. So yes, this is what it means to prototype and test your circuit, and of course you will keep reiterating. I also would like to add that before I prototyped this, I actually drew out a schematic on paper. And then I sort of followed that schematic. Schematics are going to be your best friend for you and the computer. But let's continue. This is sort of like a diagram showing what I literally connected onto the breadboard. I've also included the names of the components as well. We don't need to get too much into the details as this is a PCB workshop, not a components workshop. But for your reference, when I'm talking about different components, this is what I mean. So before we start making a schematic, right, or before we even try to, I guess, understand what the connections here were made, right, so that we can translate our prototype to a new schematic to a PCB, we need to talk about, I guess, really quickly, current. And we're going to talk about some common terminology. Just so that we're all on the same page, I'm going to talk a little bit about what current is and what to expect from a circuit and a schematic, I guess. So when we're making a circuit, we're trying to create a path for electrical current to flow through, right? So let's say if this wire didn't exist, right, then there would be no path for that current to go through the resistor and through the LED and back to the negative terminal. Here's another thing. Just because things are connected doesn't mean that current is going to flow. The path has to, I guess, go from higher voltage to like what we call ground, which would effectively be 0, right? So if this was plus, but this was also plus, because there's no difference in between the two charges, current isn't gonna flow. I hope that makes sense. But let's talk about why this works. So a breadboard has got ways where you can connect your power, right? Because again, power is really important because that is what is actually going to generate current. It is going to drive that current to want to get from A to B. You know what I mean? And here we have our circuit area. You'll notice that there will be these lines going in the vertical direction in our case, whereas the power rails are going horizontally. What that means is that everything along this line, everything that is along these continuous lines is connected to each other, meaning they will share the same connections. Again, connections are really important because if you don't have a connection, then you don't have a path. So for example, if I put, I guess if I apply a certain signal or voltage here, that doesn't mean that this is going to get the same voltage, right? You have to create that path. However, this little dot, I guess, this pin has the same signal as this pin, right? Because they are connected. So yes, very important. That is how, this is the skill that we're going to use to interpret the breadboard diagram. Okay, before we make our schematic for our PCB, let's talk about ways that schematics can be organized. So here's an example. Usually a dot will indicate that I guess these lines, right? Because we feel like using lines to indicate that components are connected. It's like a very natural thing, right? It's sort of like connected dots. Um, However, because oftentimes there will be not a lot of space, or not that, but just like there can be overlap. Convention will be to use these dots to indicate that yes, there is a junction here, there is a connection here. Whereas overlapping and crossing would just be like, oh, don't worry about it, these aren't actually connected. You see what I'm saying? However, you can imagine that this can get pretty messy pretty fast. So, uh, a common thing to do is to actually assign, like, draw a connection out to like a flag, or this is called a flag or a net, or in this case, since it's referring to power, it will be like a power node. And now this is sort of like an abstract representation of a connection that then we can use for the rest of our circuit. So if you notice, this is connected to 5 volts, but this is also connected to 5 volts, but this is also connected to 5 volts. So that means that all of these are connected to each other. They're all connected to the same node. And this is something that is used really, really frequently. But why stop there? When you have, like, I couldn't get rid of the lines for this picture, but you doesn't have to stop at just power nodes, right? It doesn't have to stop at just voltage and ground. If there's like signals that are being applied to like different parts in your schematic, you can sort of recycle the flags as well. For example, this TX0 is connected to this TX0 here, even if there's no line going between them. Because they share that same common point, they are connected to each other. So that's just a little crash course on connections and schematics for you. Let's keep going. So now what we're going to do, right, is we're going to draw a schematic. And the reason why we're going to do that is because in your PCB design software, the first thing they're going to ask you to do is to make a schematic, because the computer then is going to use that information to convert it into PCB. I hope that makes sense. So, yeah, I just think that having your schematic in mind really helps when you're doing it, if that makes sense. And it's gonna help us follow along. We're all gonna be on the same page. Okay, I'm yapping. Let's go for it. I've also included these symbols on the screen here, so I'm going to be using these, and we're gonna walk through this together. So I'm going to open up Microsoft Paint. I don't want all that. Okay, let's start it. So, also I'm on mouse, guys. So you know. Okay, I like to start with my power connections, obviously. So let's just draw a cute little battery here, right? You're like, where are you getting this symbol from? I've included over here. So a battery can be like a DC, a direct current source, but you can also denote that it's a battery like this. But you know, we're just gonna leave it like that for now. Okay, it don't matter. Weeball. So okay, and let's connect this to, let's say this is 5 volts. I know I have 4.5 here, but like I'll put, well, okay, happy. And now of course this is our ground. So okay, we have our first connection set up. Now let's see where this is going, right? Again, we have this power rail, meaning that the positive terminal from this battery is connected to all of these pins. And then covered it here, we can see that I also connected this rail to this rail. So now all of this and all of this is connected. So let's go for it. All right. Yeah. Start with what's connected to our power, shall we? So you'll notice that we have this wire going into this pin of our chip, our integrated circuit. And we also have this resistor going to this pin. And then if we go down here, we can also see that our next connection is going into here, into this pin of the IC. So I guess let's start with that, right? We can draw our integrated circuit, if that's okay with everyone. But how are we supposed to know what pins are what, right? Okay, let's talk about it. So this is a very common convention, right? Having like a little dot printed, or not printed, but just like a dot on the IC to indicate this is pin number 1. And when we're counting pins, go from 1, 2, 3, 4, and then across, I guess the last one on this side will begin 5, 6, 7, 8. Now we know what our pins are. Let's review what pins are connected to power. So 1, 2, 3, 4. 4 is connected to power, so okay, write it straight down. 4. And then 7, right? Because 5, 6, 7, and then 8. So let's go for that, shall we? I'm gonna put this. I don't like the size of this. I need to get bigger. Sorry. Nope. I don't want 7 here. I'm gonna put 7 here. I'm gonna put 1 here. No, I'm gonna put 4 here. Sorry, not 1. That was 8. And it'll make sense in a second. But yes, you can see how like just write down pin numbers and then put them wherever we want on the drawing. That's because we know what pins relate to what, right? As long as we're able to represent the connections in an accurate way, the position doesn't matter, if that makes sense. So let's keep going. You'll notice that I decided to put 8 and 4 towards the top, and also 7. The reason for that is because they're closer to power than they are to ground, right? And that'll make organizing the lines in the schematic a little bit more natural. So speaking of ground, let's talk about that, right? So it's connected to our ground. We've got this third terminal, the potentiometer, this capacitor that is going into pin number 5, and then we go around, and it's also pin 1. And then also this, sorry, did I say capacitor here? I meant potentiometer, and this capacitor pin is also connected to ground. Not too worried about the potentiometer and capacitor right now. We can leave those for later. Let's just wire up these two, this capacitor and this pin. So I'm gonna put pin 1 and pin 5. Also, I know this is my output pin, so yeah, let me just grab this over here, put it more in the middle. My output pin is number 3. I just know that already, so I'm just gonna write it down here. And then I'm going to write 2 and 6. And it'll make sense in a second. But okay, I just want to get that out of the way. So we've got our 1 that is going to ground. And then we have our capacitor at 5 going this way, right? And it's all going to ground. Very cool. Okay, that's that. Oh, right, and of course, these 4.5 volts. And then have this resistor, right? That is connected to 7, right? Do we agree with that? This end is connected to power, and then this end is connected to 7. Cool. Alright, yeah, I guess since we're here, let's go ahead and start tracing out the rest of these lines. So we have this wire that is going from pin 7, aka also the end of this the end of this resistor, right? And it's going to go into this terminal of our potentiometer, right? So let's go see what that's about. Our second terminal of the potentiometer is connected to pins 2 and 6. That's why I wrote them down together here, because I kind of knew that, guys. I cheated a little. But, okay, so we know from here we're going to start talking about a potentiometer. So let's go ahead and do that as well. A potentiometer, you'll notice like in this sign, it's sort of like a resistor, but with a little line in there. Do we agree with how we did that? I wrote this arrow here because it's this middle terminal that is connected to pin 6 and 2. So that's why I did that. And then let's talk about our third terminal. It's like this is also connected to ground. Okay, let's go ahead and just connect it to ground. What else is connected? Well, here, if you'll notice, since this is sharing the same row as where 2 was connected, that means that the end of this capacitor is also connected to 2. So let's talk about that. And then you'll notice that this capacitor has a different sign from this one. That's because the polarity of the pins matters. So let's just go ahead and do that. And then this pin is connected to ground. Cool. It's ground and ground. We got our thing going on here. If you're interested in why this schematic is wired the way that it is, we do have a fun interactive demo coming up for you guys next week, so please check that out. But anyways, let's keep going. Now our output pin, right, pin number 3, it's going to go to the positive terminal of this LED and then flow into a resistor and then back to ground. So let's just get that out of the way. I'm going to draw my LED with the little arrows to indicate that it's the light. And then a resistor. And then, okay, this is our finished drawn up schematic. I hope we're fans of it because we're going to refer to this for the rest of our workshop. Yes, we made our breadboard prototype and we verified that the circuit actually works. And we made a schematic. Now it's time to make a PCB from this schematic. So we're going to talk about 2 platforms. We're going to talk about EasyEDA and KiCad. And the reason why is that they both, I guess, have different use cases. I feel like both are worth learning, especially since a lot of us are starting out in our career. So let's talk about the differences between the 2 suites real quick. So EasyEDA is going to be the first one that we're going to get into, and the reason why is that it's a little bit more beginner friendly, and it's also easier to order PCBs from EasyEDA because it's integrated with JLC PCB. EasyEDA is web-based, so your designs will be stored on the cloud, and you can also collaborate with people in real time, and as well as access their vast library. That's something that I didn't mention in this bullet point here, is that EasyEDA has just a vast user contributed library where people can upload footprints and symbols for different components that KiCad might not have. But again, so if you just want to make a PCB and get out, EasyEDA is a really good option. It's just a real time saver, and it's also pretty intuitive to get into. Yeah. KiCad, however, it is a desktop application that I recommend you install. It's also open source, meaning that you can install plugins for KiCad that will that will match your productivity or match your workflow. And again, because it is you're editing a file on your computer, it's a little bit more difficult to collaborate with other people over the web. But yeah, since it's an application and it's meant for I guess heavy work, you could say, there's a lot of tools that it has that EasyEDA doesn't have or has a smaller version of. But of course, since there's just so much customization and control that you have with KiCad, because it does give you those liberties, their learning curve is steeper. And also, due to it not being connected to the cloud, you won't have access to user contributed libraries at your fingertips. There are libraries that come with KiCad. You can also get some online, but it's just not a lot of stuff isn't embedded into the software. You would have to come up with that yourself. Alright, let's start talking about EasyEDA. I'm here in my browser and I just opened up the standard edition of EasyEDA, so let's do that. We're going to start by making a new, make an account if you haven't, and open up the standard version. And then now we're going to make a new project. Let's just make a new standard project. We're going to call it 555 timer LED blinker. Okay, you'll notice that now you've created a project and you have a new folder on this side, and it comes with a schematic already. So you can rename your sheets, right, for documentation stuff. If you feel so inclined, you can just say 555 project or something, and we can get started. So again, this is why it's really useful to already have your schematic in mind. I'm gonna go ahead and maybe not split screen, but just like that. Alright, okay. Yeah, let me just put this on here really quick. If we want to start putting components on our schematic and stuff, that's when we'll go to the library. Common library has common parts, but the library feature that EasyEDA has is really useful because this is where you can access the user contributed libraries, and you will also get previews of footprints and stuff that will come with it. So it's really fun and riveting stuff. Let's go ahead and search up battery because we do want that, battery, device, battery cell. And you'll see that it comes with a symbol, right? And also a footprint. So a footprint is an actual is a representation of what is actually going to be printed onto your PCB. So squares like this indicate that a component is going to be surface mounted, But since we're all beginners here, we're going to look out for components that have holes because those are easier to solder. So yeah, look for something that we're a fan of, right? Like we can just grab this. I'm sure we have stuff like this that's a lot. I don't know. Way that. You know what? Yeah, you can just grab whatever feels right to you. Notice how this has a symbol, but it doesn't have a footprint. We can try to just like move more towards what we like a footprint because that saves the time, right? Sure, you can grab the symbol from here, but then you're gonna have to assign a footprint to it later. So it's just kind of because it's a battery. You and God or whatever knows what you want from your battery. All right, so yeah, notice that I like just clicked my component and then I clicked on the screen on the schematic to place that component. So we can just keep doing that and we can keep going. Let's talk about this 555 chip. We can search up 555 timer and again just start previewing what we've got. And again, notice how we're getting stuff that looks nothing like our timer. These will help you out, but also usually like people know what the people want, right? So now you're going to start looking at stuff that is more related to you. Oh, I'm a really big fan of this because it's got our power like down, and then also the footprint is very cute. I haven't seen this before. I'm gonna go ahead and place this component here, and let's just keep looking for stuff. Let's see, resistor, right? We just want a basic resistor. See, this is surface mount. We're not gonna do that. Just choose something we like. I think this is good. I've like before. The symbol is so tiny. Let's just grab this. I think we'll be okay. Or sorry, I'm just curious. I'm so nosy. Bro. I'm just gonna go with this. Boop. Alright. And let's get a potentiometer. Also sometimes systems has really good options. Let's check it out. They're pretty common. However, I just organized the entire IEEE lounge. We have more stuff that looks like this, so we can just, yeah, this should work fine. We have plenty of these. I'll put that on there. Now we've got a capacitor. See, no footprint. This has got a footprint. Okay. It's cute. So this is an electrolytic capacitor. It'll work just fine for this one that we've got over here. But we can get this one, which is the non-polarized capacitor. And of course our LED. I like to search for LED 5mm. And then let's see. User contributed. That's good. This will work lovely. Alright. I think we're done in terms of all the components that we got. So let's start putting them in a way that we actually like, right? Potentiometer, just dragging all this up here. Okay. I'm gonna take advantage of the flags that we were talking about earlier. So I'm going to, again, I went to this wiring tools box that's over here and I grabbed this. It's called a net flag ground. I clicked on it and I'm gonna place it over here. Is it connected? No. See, like when you click on the component, you can actually see like the little gray circles. That's telling you that the connection is going to be made there. And when you hover over a component and like it illuminates a dot, that's the computer trying to tell you, okay, connected here, I will recognize that. I will acknowledge that. So let's do that. Connect. And then I'm gonna grab this flag that says VCC, and now I'm just gonna put it here. I also like to just like things around, like a little shake, and it follows around, but it stays connected. That's how I like to see it's connected. You know. Now we have our power for the battery connected to this flag, and the and the ground from this battery connected to this flag, meaning that anything else that is connected to these flags is going to be directly connected to the battery. Boom. So that's pretty efficient. Let's keep going. We're going to start with our timer, just like how we did in our MS Paint example. And yeah, let's make those connections. So, where's that circle at? Hello? Oh, there they are. Hehe, okay. You see? Wire spawned, boom, connected. Let's do the same for ground. Boom, connected. There's other ground here, but you have to stick to using the same symbols. If you use a different symbol, I'm not going to recognize that. But yeah, keep going. You know, just for funsies, I guess, let's talk about, you know how we talked about net flags earlier? we can click on this icon and generate a label. And now we can use this label in other places. So for this one, right, I'm going to connect it to pin 3 because this is going to be our output label, just so we can use that later. Sorry, I'm just trying to clean things up. Okay, and then now here's a trick question. Well, not a trick question, but here's a question. Since I know I want to connect my potentiometer after this resistor, where should I make the connection? Should I drag it out this way? Or should I drag it out this way? The answer is that it's going to be this way, because you'll notice that if we connect it like this, it's connected to our VCC. But if we look at our example schematic, that is not what we want. We want it connected to 7, not VCC. So let's keep it going. Oh. Let's keep it going. And look, guys, I'm not a professional. I'm sure there's a professional watching this being like, oh, this is so whack. But it is what it is. So yeah, the reason why I did that is because I noticed that our symbol was like all the way over there, and I was like, and I was gonna give it a little flag. So yeah, 2 and 6 are now connected to the same terminal of the potentiometer, and the third terminal of the potentiometer is connected to ground. Looking pretty accurate. What else are we missing? This is also tied to our electrolytic capacitor, so let's take care of that, shall we? Let's go in here, and okay, so I did some off-camera mining, and by that I mean I've gone ahead and just like wired this up so that it'll match what we've got here, right? You know, just creating more room so that we can connect our capacitor and our flag and our 6-pin, connect our 6-pin to our 2-pin, and then also, since I forgot about these pins, I'm not gonna lie, I just added this our capacitor. I'm not too concerned about the numbering here because I'm going to use unpolarized ceramic capacitor, so like low-key it doesn't matter. And then this, our power is tied to our pin 4. Now I got that. All that's missing is to connect our output pin. So let's do that. Wait, whoops. See, that's not gonna work because it doesn't have the exact same name as output, right? Very important. And then I'm gonna copy paste our resistor. Press R to rotate. Okay, and here's our EasyEDA schematic. I'm gonna go ahead and minimize this. We don't need it right now. But this is what our software is working with. So let's go ahead and Control S to save. And now that it's saved successfully, we can go to Design, Convert Schematic to PCB. Okay, now we're here. In our new PCB thing, you can sort of change the shape of your board, right? Let's go with circle. Why not? And then copper layer. For most beginner projects, you can just go with 2. 2 is fine. 2 is good. The significance of that is that you can actually place components on different layers. So that's fun. Okay, let's get into it. So what is going to happen now is Oh wait, why is this resistor massive? What? Why is it so big, enormous? Okay. Mm, I don't I don't think it should be that big, enormous. Let's just find a different one real quick. Okay, wait, I'm not a big fan of these footprints actually. So what I've done here is that I'm going to go back to my schematic. I'm going to click on the component of the footprint that I want to change. Click on footprint and just look for something I like. You can Control S to save again. Control S to save this, but then also design and import changes so you can see how our resistor changed. Now it's smaller. I don't know if it's just me. I feel like it is like unreasonably large. Am I not the only one who thinks this way? Okay, some more reasonably sized stuff. Yes. Alright, let's continue. Okay. You'll notice that we've got these lines going around. These are called rat lines. They'll sort of tell us what the computer recognizes as what needs to be connected to what. So for instance, if I highlight this pin, it's gonna show you what other pins are connected to that. So very fun and interesting stuff. When it comes to PCB design, something that we want to do is we want to minimize our trace length. So yeah, let's start doing that. I'm going to arrange my components here in a way that sort of keeps things that are connected to each other in a similar place. And I will come back and let y'all know what I've done. Okay, so what I've tried to do here is like I've connected my like positive trace, or yeah, there you go. So all those pins are connected to each other, and here's my ground. If it will illuminate, there you go. So all of that's connected to ground. So power, and then this resistor, and then our metal terminal, and then again also ground, and then of course our output. Just doing that. So yeah, I think I'm gonna leave it at. Here's a fun opportunity. If I like when the PCB will render, it's this is sort of like its border, right? So for instance, if I save this and I click 3D, you'll see how that battery part gets cut off. Very interesting. Um, I'm just gonna leave it at that. I'm gonna be honest, you guys, I wouldn't put this here. In fact, let me just change the blueprint at this point. Yeah, there you go. Save and then design, update. And then, of course, you can also add text. Maybe put it on your silk screen layer. So yeah, let me talk about this a little bit. So there's different layers. I know we talked about copper layers, as in like you could put components on one side or on the other side, but there will also be different layers for silk. It's probably one of the more important ones. So silk just refers to the actual labeling on the PCB. So now, also the neat thing about EasyEDA being connected to the cloud is that it also has an auto router. So if you click auto route, it'll just go ahead and do that. And also, here's some design rules, right? A really common practice is to make your like power and ground to like have even more, sorry, thicker traces. So let me do that. Okay, so now we've generated PCB in EasyEDA, and obviously there's ways that you can improve this design, right? For instance, you could go to check the RC, sorry, not check the RC, design rule, right? And then you can go ahead and add like different requirements for like track widths and stuff. Um, I'll include like values on the screen that are like generally standard, but yeah. And then you would just, and then you could click on which net you wanted, apply setting. Oh, and then you could go ahead and auto route that again. It's going to check the design rule again. You can also do it directly from there, but then go ahead and it'll rerun. And then yeah, it'll update that based on the design rules you added. Pretty neat stuff. So now that we know how to use EasyEDA, right? Let's go ahead and use KiCad.